Sorry about that. I thought I had the recording going. Okay, so to back up again, we started with 2D coordinates, and we're going to talk about some coordinate calculations. I'm going to touch on state plane. We didn't talk about it last week, and there's a lot to state plane that you guys don't necessarily have to know about, but I just wanted to show you some of the finer points of it. So we talked about the concept. It's a very powerful tool, and we're going to see a lot more how that works out, and I hope that you're starting to do some of this homework so that you can kind of start to get the idea of how it works. But all of the labs that we will be getting into will really be dealing with this coordinate concept. So as we develop more of those, we'll start to see how that comes into play a little bit more if you're still not totally on board with it yet. Let's see. So there are several types of coordinates that we should be aware of. Like we talked about ground coordinates, terrestrial. That's primarily what we're working with as a ground. We're working on the ground surface, but we kind of project everything to a plane. So you might call those terrestrial type coordinates. And you have geodetic, that's latitude and longitude, and then plane coordinates. And the primary type out there is what they call state plane. There's another one called UTM, which I didn't even talk about, the Universal Transverse Mercator System. So that's a bit different thing, but that's also a planar system, which is a worldwide system as opposed to just a state, individual state. We looked at this, the 2D, the 3D, and the hybrids. We didn't talk a lot about hybrids. I want to show you a little bit more about those today, but two-dimensional, Cartesian, rectangular, and polar, that's kind of what we're dwelling on the most right now. We will see this 3D concept a little bit more later as we get into it, but we're primarily going to be doing a lot of our horizontal layout with just this 2D, two-dimensional, and rectangular system, or polar, because we use a lot of those both back and forth. So I did talk about the polar to Cartesian conversions, and again, that's important, but we're going to jump into a little bit more of the inversing stuff today. But there's your equations are there. Coordinate geometry. This was showing you how a three-dimensional coordinate would work in terms of rectangular. That's a rectangular, or Cartesian, X, Y, Z. That's a three-dimensional polar coordinate, which is actually called a cylindrical coordinate system. And then, of course, we have the spherical, and that's again what your primarily your instrumentation is using. So let's go into the hybrid. The hybrid I'll talk a little bit more today out, but that's you can think of it basically as a rectangular system, but it uses this concept of what they call station and offset. So it's just a little bit different how it works. So let's talk about the inversing a little bit. So there's a couple of routines, and these are the things we want to focus in on. I just want to work with you guys a little bit today on this. The inverse routine, can anybody tell me what I mean by an inverse routine? Or when I say the term inversing, what that really refers to or means? We spent all week last week on nobody can tell me what that means. All right, so an inverse routine is a concept of where you have given coordinates. You're given a northing and an easting of one point, a northing and easting of another point. And from those, you can determine a distance and a direction or direction, because you don't always need both. So if I have a northing and easting, or X and Y at point 1 and a northing and easting at point 2, I can tell you what the distance between those 2 points would be, or the direction. Okay, so that's what we mean by inverse. Direct is kind of saying, all right, I have a known point, and I've got a distance and an angle to that point, to an unknown point rather, and I can tell you what the coordinates are on that. So we kind of primarily were working about those. Angles are basically saying I can get an angle if I have 3 points. Basically, I would inverse. I'm going to show you this concept today. We'll talk about this because we didn't do this in class the other day. So intersections are very interesting in how they work. They're a little bit more mathematical, but these are ways of getting coordinates at points that you don't actually occupy. So you have what's called a bearing, a bearing distance, and a distance. So let me just flip over here a minute and we'll go through all these real quick. And then we're gonna do some problems. So, and particularly problems if you want to work out anything.
I have a question real quick
I'm
about
sorry,
inversing.
question?
Yeah, about inversing real quick. Yesterday we were using a GPS and
Uh-huh,
we were plotting out somebody's backyard because they want to put a pool in. And
yep.
they had these big pine trees in the backyard. We wanted to get the base of the pine tree, so we held the GPS out. We'd put an engineering tape measure to the base of the tree. We'd hold it out past the pine trees and say, like we put the code in and we'd say four off, 4 feet off. Is that considered inversing as well too?
Well, actually, no. What you were doing was doing a location, right? You were locating the point.
Yeah.
So you were basically doing what's called a direct routine. Okay. So here, let me draw these diagrams, and I think that'll explain it to you. Okay. Primarily, well, with GPS you can do both. Just understand you can do both layout. Okay, that would be more direct, and then the other one would be inversing. Kind of do both. So it's a little different. But what you are being provided is coordinates. Okay, at the end of the day. So here's an example of a direct routine or an inverse routine. Okay, let's say that's a point. So, or that's a line, and we have a coordinate here of a northing and an easting. So we know these, okay? That's what I'm saying. That I know that point and I know this point. So I have, let's say this is point 50 and this is point 51. So we know what the northing and easting is here, and we know what the northing and easting is here. Inversing says you can determine the distance between those 2 points. So I could tell you what that distance is. I can also tell you what the direction is. Okay. Now, you were basically saying you just had a tree out there somewhere, right? You just wanted a coordinate on it. Is that right?
Yeah.
Yeah. So that's a little different. You see how that's different?
Yeah.
Okay. So this right here is with the concept of inversing. Okay. So you know the coordinates here, you know the coordinates here. You can solve that, and you can solve that pretty easily. So we did a lot of that last week, and I'm gonna do some more problems with you because we need to hammer this home a little bit so that it becomes almost like second nature. Okay, so that's an example of an inverse routine. So a direct routine, which is kind of more what you were talking about doing, is you had a point you're starting at. Let's see if I can back this up a minute. So let's say I've got a point out here that I want to locate, but I don't know it's northing and I don't know it's easting. So those are unknowns. Okay. So what I can do is if I know this point, let's say this is like point 50, and we have another point we can backsight. Let's say I got another point sitting out here that I can backsight. So if this is a good alignment, what I'm going to do then is I'm going to measure an angle. Okay, so I'm going to measure an angle, and I'm going to measure a distance. So by knowing this angle that I've measured, by knowing that distance, and you have to recognize the fact that this has some kind of azimuth or bearing to it. So this is a known point, 50 to whatever. You measure the angle off of that. If you know this azimuth and you know this angle, you can solve this azimuth. And if you know that azimuth and you know that distance, then you can solve the latitude, which would be in this direction, assuming north-south departure. So by solving this vector and that vector to that point, this we can call latitude, this we can call departure. By measuring the angle, measuring the distance, knowing the azimuth, and knowing the coordinates, I can determine all of this, and that'll ultimately get me this. So this process is what we call an invert or a direct routine. Okay. That's more or less what you were doing with GPS, except you weren't backsighting anything. You were just using the satellites that knew all of this, so that they were basically giving you a coordinate. So it's a little bit different, but what you're getting out of it was a coordinate at the end of the day. Okay. And we didn't do a whole, well, we did this actually when we did side shots. So we kind of used both methodologies when we were doing our side shot problems, because when we were doing our side shot problems, if this was a traverse point, and let's say this was traverse point 51, we had to determine the direction from 50 to 51 using an inverse routine. And then we used a direct routine with the angle and the distance to calculate latitude and departure. Okay, so we actually did both things last week. And what I hoped you did for homework, and we'll see how I'm going to work some of those problems on this thing. We'll see how we get with those. So the other thing I talked about in the PowerPoint was you can get an angle, and actually you can get an angle and a distance. It's just kind of still using the inverse process, but here's what I'm talking about. In any typical project where you have control, give me a sec here. So we have control. Let's say we got a control point here, and a control point here, and a control point here. So let's say this is control point 1, 2, and 3. So in this process, let's say you have a building out here that's not staked out yet, but you want to stake it out because you need to put the foundation in and all that stuff. So your engineers have calculated the positions of the corners of the building, and they have given you good northing and eastings for each of those points. So we have northing and easting on each one of those. Northing and easting here, northing and easting here, here, and here. So just remember the building at this point doesn't exist, but we have our control over here that is related to the same grid system, the same northing and easting system. So what this allows us to do is lay this out using my ground control. So what I would do is say, okay, I'm going to occupy 1, backsite 3. I can inverse that line. That'll give me the direction here. And then I can inverse the line from 1 to that corner. So if I get this direction and that direction, it allows me to determine the angle that I need to set this corner. And then I can also calculate the distance. So this process where you're calculating angle and distance, angle and distance, angle and distance to each of those points, we call this process radial stakeout. You might be, it's not a very good picture, but all of these lines are radial to the same point. Now, it might be easier to get these 2 points from setting up on another point. So this is a process called radial stakeout. So if you were using a GPS system, instead of having a control network like this on the ground, your control network is your satellites up in the sky. You still have this given, and that's given, and that's given, and that's given. And then the satellites position you into that spot. But they're not going to typically position you quite as much because you're going to have centimeter accuracy as opposed, you're going to get a little bit better accuracy on these kind of things. So it does make a difference what you're doing. It's just all relative. So we're gonna look at this process today, which really uses that concept of inverse. That inverse is so powerful, you kind of use it all the time. We use inverse, and we use direct. And between those two, we can get that radial stakeout, what we call radial stakeout. Okay, so those are some things, and we'll touch on those here in a minute. I'll do some math problems with you here so we can kind of see it. And I would like to back up and do some of that homework just to see if we are on the same page with that. Let's go back to the PowerPoint. So what we just defined there, we just talked about was inverse routines, direct routines, and angles. So these guys called intersections are really interesting because what they allow you to do is calculate coordinates of points that you actually cannot occupy. As I think I mentioned the other day, like a radio tower, top of a radio tower, you're typically not going to set up on the top of that, but you might need the coordinates of the center of that. So I'm going to show you a way you can do that using these concepts that we just talked about. So again, I'll draw a little diagram here. So if we use what's called a bearing-bearing intersection, that implies that you have a bearing, two bearings given, and what you're going to do, you're literally going to intersect 2 points that you have lines on. So for instance, here's what we're saying. I know this coordinate. So let's say this is coordinate 1 or point 1, and he's got a northing and an easting. And you have another point over here, point 2, and he has a northing and an easting. So both of these are known. So you have a point out here. Let's just say it's a manhole. And we don't know what its coordinates are. So we could shoot a distance and get a direction. We could do a direct routine, but direct routines don't always work for different reasons, obstructions or something maybe. But if you sat at 2 and you measured a direction to that point, and you set at 1 and you measured a direction to that point, where those 2 directions intersect, we can call this either a bearing. So this would be the bearing from 2 to the manhole, and this would be the bearing from 1 to the manhole. We don't even need to measure that distance or that distance. We just shoot that bearing and that bearing at each other, and what you get is the location, the northing and easting of those points. Now in AutoCAD, you do this all the time. Does anybody know what command or commands would do this for you in AutoCAD? This very same thing.
Is it intersect?
Is there a command called intersect in AutoCAD?
Yeah, I believe so. I mean, it's been a while since I've used it.
Yeah, I don't think there is. There is one called extend. Is that what you were thinking about?
Possibly.
Okay, there's an extend command. That's doing that. So is the trim. Okay. And the other one that works very well is fillet. These guys are all pretty much doing this process right here, as long as fillet has a radius equal to 0. So if you set your fillet to a value other than 0, what it's going to do is it's going to put an arc in here. Okay, so that's not what we're after. So this process, we're not going to have time to do these kind of things, but this is a process that you pretty much use a lot when you're doing solutions for things. Maybe more in the office than you would say out in the field, but you could do this. So this is called a bearing-bearing intersection. So the other process that was mentioned there, let me go ahead and do a new one, was a process called a bearing distance intersection. So this guy's a little different. Let me show you. What you're doing is you're intersecting a bearing and a distance. So what we're saying when we do this, and if you're interested, there is in chapter 15, your author goes over the math that you do this. These get a little involved mathematically, but it's not that big of a deal. But let's say you have a bearing right here. So this is a point. You know this point. Let's say again, you're maybe say at point 10. You know this guy's northing and an easting, and you know this line's bearing or azimuth. You could use either or. I just choose to use that. So we know the bearing on that line. So you have another known point. Yeah, let me do this. So in this case, I have another known point, that's sitting in the center of this circle. And so what I actually know is the radius of this point. And the radius refers to your distance. So what happens here, let me see, if we intersect this circle with that bearing, we get a solution there, or we get a solution here. So this type of intersection can yield, we could call that point P or point P prime. So we could do either one of those could work. Now again, what I forgot to mention, we know this point 50, we'll call that the northing and an easting. That is the center of the circle. So we know the center of the circle, we know the radius, and we know another point, we know another bearing. So this is a little bit higher level type of intersection. And again, this one, unlike the bearing-bearing intersection only yields one solution. This has the potential to yield two solutions. And so if you do this problem, you have to know which one you're talking about. Am I talking about this one or this one? Because I can get both of them. And so maybe I don't want that one. That's the one I want. Okay, so that's called a bearing distance intersection. And again, this is a process we use in surveying quite a bit. The last type of intersection is called a distance-distance intersection. So what you've got is one circle, you've got another circle, and you know the center point of this circle. Let's say you know that guy's radius point. Let's say that's 50. You know his northing and his easting. You know this circle's center point. We'll call that 51. You know his northing and his easting. Where these two circles intersect, saying again, assuming you know radius 51, and you know radius 50. So we know that distance, we know that distance. Where these two circles intersect gives you two solutions. Again, you could talk about either that point or P prime. So this is the type of intersection that will also yield two solutions, and this is referred to as distance-distance intersection. So all of these things are used, we use these all the time. Again, you can do this kind of stuff in AutoCAD. Essentially, you can draw two circles and figure out where they intersect, and then you can either snap that intersection or snap that intersection. And you might have been talking about an intersection of snap, by the way. And that also, you were right, that would give you a solution. Okay, so those are other types of coordinate calculations. We're not going to get into these, but these are covered in chapter 15, and just to show you that they're out there. So the last thing I do want to talk about today, though, is determining area with coordinates, which is kind of interesting. So I want to do some inversing. Well, actually, I want to see, does anybody have any questions on that homework? Because I would like to definitely go over that. Let's start out of chapter 14. There were problems 1, 2, 3, and 4, and I mentioned those the other day in class. I don't know if anybody had a chance to go back and look at them. Did anybody do that? Anybody out there?
I didn't do the problems in the book. I did the handouts though.
Okay. All right. Well, let's start there. Are you talking about the side chat problem?
Yeah,
Okay.
the one that we partially did, and then the other ones.
Well, let's look at the one that we didn't do. Okay. So I gave you. Let me just. I'm not going to do all of this, but if anybody wants solutions, I can certainly give them to you, or even post them. But let's. For the second side chat problem, it had a four-sided traverse, and there was a point 10, 11, 12 that we needed to solve for. So what I'm going to do right now is just solve for point to 11. So let me draw a little sketch of what we're looking at. We'll label it and then we'll go through it, see if there's any questions. Let's see, we were sitting at 3 and backsighting 2 kind of looks like this. And then we had a point up here that was point 11. So this isn't to scale, your picture's to scale. So this is 2. And this is 3 down here. And then this is 11. So let me label what we had. Point 2 had a coordinate of 1279, 68, and 1018, 13. You know, this is a little tough to do. Those are in terms of northings and eastings. And then we've got 1197, 70, and 735, 31. So the diagram indicated that you measured a field angle to 11, which was 308. Zero 2. We didn't do this in class, right? We just did the other sheet, right?
Yeah, we didn't do this one.
Okay, all right. I just didn't want to be redundant. So this is 6424. Okay. So who can tell me, we need to get this point right here. So is this a direct routine, an inverse routine, or both?
Direct routine.
It is that, but you also need to know what? The backsight direction here.
Yeah.
So in order to do that, we have to do an inverse. So we kind of are using both, okay? All right, so did anybody solve this by any chance?
I did 10.
You did 10? All right, well, we'll do 11. Okay, that's good. What'd you get for 10? Just out of curiosity.
For which one?
You said 10, I think?
Yeah, so my bearing was 7350.06
For the backside? Are you talking
for
about
the
the same?
backside.
I didn't get that.
Oh, well,
You backsighted 2?
I went from 2 to 3
Oh, well, it
because
doesn't.
the direction of the arrow. I didn't know if I got that right or wrong.
No, you didn't. You're talking about getting to 10, right? You said?
Yeah.
Okay, if you look at the diagram, you're actually backsighting 1.
Okay, so the direction of the arrow doesn't take effect until.
No, okay, now I know what you're saying. This is the arrow head, this is the tail. You actually know, you have to go to where the tail is. This is the line you want. The arrowhead's your foresight. The tail is your backsight.
Okay.
Even so, if you look at your diagram, you were down here. That thing's coming around like that to 10.
Yeah.
Okay. All right, so, well, we can do that, but your problem's going to be wrong if you inverse that. Okay.
Well, we can finish 11 and I'll go back and do 10.
That sounds good. That sounds real good. Okay. All right. So what do we do first?
Shall we be finding the northern
Of what?
11?
We do. We want northing and we want easting both, but we can't do that. That's the absolute last step. So what's the first step?
We need to find the bearing
We need to find the bearing of what?
of 2 to 3.
Of 3 to 2.
3 to 2.
Yeah, you're sitting here.
Oh, yeah, right. Yeah.
See how my arrow is pointing?
Yeah.
Correct. So we can use this in terms of bearing, and then we can convert that to azimuth. That's correct. Okay.
Yeah.
That process, that's an inverse because we have coordinate at 3, coordinate at 2, right?
Yeah.
So what we're going to say is the latitude from 3 to 2 is the northing of 2 minus the northing of 3. So notice what I'm doing, 3 to 2, that's where I'm sitting, that's where I'm looking. Sitting and looking, but you reverse these, okay? And we do that because that gives us the proper quadrant, okay? If we reverse that, we'll get the right absolute value, but we're going to get a quadrant issue, okay? So let's see what we come up with. You guys verify what I've got. I'll write down mine, and then we'll see what we got. I got 8198.
That's what I got.
And that's a plus. Anybody getting that number?
Yes.
Okay.
Yeah, I got that.
What does the plus indicate?
It's north of us.
Correct. Right. Because if it was negative, it would say 2 was south of us, right?
Correct.
And if we look at our picture, I drew it like it is on that diagram, and that's assuming north is up, okay? All right, good. So departure 3 to 2 is the eastings. So in this case, it's easting of 2 minus easting of 3, okay? So that would be 10, 18, 13. Make sure I didn't transpose anything also. If anybody sees a mistake, it's probably on my end. I have a plus 282, 82.
Yeah.
Yes.
And again, what does the plus indicate in the eastings component?
It's east.
It's east, all right. And that picture makes sense, right? So the bearing then is the arctangent of what over what?
Departure over latitude.
Latitude.
Right, and that's always departure over latitude, right? We never flip those. If you flip them, you will get the answer off of east, and that wouldn't be a bearing. So I'm going to go ahead and, again, watch me so I don't transpose anything. So it looks like I got 7350.06.
That's what I got.
That's what I got.
Okay. Anybody else? Oh, I just wrote that wrong, didn't I? 7350.06. And we also know the quadrant is northeast. So that's nice because that means the azimuth is what?
Positive.
Well, it's also northeast. It's also this. It's the same number, right?
Yeah.
Yeah. Okay. All right. So I'm going to write that here. That's 7350.06, and I'm going to call that an azimuth, so we just don't mistake that for an angle. Okay. All right. So there's your inverse. All right. That's the inverse. Now we could also get that distance, right? Could we not?
Yeah,
Could
we
we get-
could.
What? I'm sorry. Say that again.
We could get the distance.
We could. Do we need it?
No.
We don't. So there's no point in calculating something you don't need. All right. So in this case, we don't need it. I mean, sometimes we do, sometimes we don't. So it just depends on what we're doing. But we do want to know what that direction is. Because by getting that direction, then I can do a direct routine. If I know that direction, I know that distance, I can calculate the latitude and departure from 3 to 11. So how do we get that azimuth?
Should we be taking 308.02 and subtracting the 7350.06?
I disagree. Think about north is up, right? If they're coming through here, right? So all we remember what we said, if you have an angle turning clockwise and your azimuth is turning clockwise, what do you do to those two?
Add them.
You add them, okay, not subtract. Okay, so all we need to do is just add the 7350.06 plus the 308, 02, 00, and that gives us our foresight azimuth. Now what I'm coming up with, you can correct or check me. I got 381, 52, and 06. Does anybody agree with that?
Yep.
I just subtracted 360 from it.
Well, I was going to say, do we have to subtract 360? No. But we don't like to talk about an azimuth greater than 360, right? So normally, I would subtract 360. Anytime I exceed 360, I'm just going to take it off. So that gives us an azimuth of 21 degrees, 5206. Does that sound right?
Yes.
So that's my foresight azimuth. So that line I have as a question mark is no longer a question mark. That's known now. That's the azimuth of this line right here. So now that we know the azimuth and we know the distance, now we can do a direct routine. So for a direct routine, we're going to need to calculate the latitude from 3 to 11. So how do we do that?
Distance times cosine azimuth.
Correct. So what is our distance in this case?
64.24.
Yep, it's the distance we measured in the field to that point. Correct. 64.24 times the cosine of what angle? You got a bunch of angles kicking around here, right? So you got to be careful. Which one do we need to use?
The foresight azimuth.
The foresight azimuth.
Correct. Yeah. It really, what you're doing is taking a cosine of a direction. So it would have to be like either that or that. This is just an angle. That's not a direction. People will make the mistake of using that 308 all the time though, okay? So kind of watch that. Think about what it's saying. So this is actually 21:52:06. Okay. And this is going to give me a positive result, which also is going to tell me that that guy is in north direction. Let's see what we come up with. If I did this right, I get 59.62. Anybody agree with that?
Yes.
Yes.
Okay.
Yep.
So the departure then of this case would be 3 to 11. That would be the distance 3 to 11 times the sine of the direction 3 to 11. And we're using an azimuth. And that's also going to be plus. Sine. Okay, so that looks like 2393. And both of the units here would be feet, by the way. Is that correct?
Yes.
Yeah. Well, we have to assume, we don't really know that, but we do know that we measured the distances in feet. So you got to understand that your coordinates are probably in feet. I mean, it would be crazy to be working with meters on your coordinates and then be measuring things out in feet. That would be such a place for error that would not fly. So those are definitely feet though in this case. So what do we do with those?
You would add them to the existing coordinates of 3.
Right, so the northing of 11 is what we're saying is equal to the northing of 3 plus the latitude from 3 to 11. So it's pretty logical. And the easting of 11 is the easting of 3 plus the departure, 3 to 11. So if we take the 2393 plus 735.31, I get 759.24. And if I take my 5962 plus my 1197.70, I get 1257.32. So those are the coordinates then that we're after. So we just solved that. Okay. So everybody okay with that?
If you're going counterclockwise,
Mhm.
instead of clockwise, how this one is, you would subtract the azimuths.
There's a counterclockwise one on there. Do you want to do it?
Yeah, if we have time.
Yeah, no, we got plenty of time. The azimuth you wouldn't subtract. What you would subtract is the angle. Okay, if that makes sense.
Yeah, that makes sense.
Okay, let me draw that. Okay, and we'll do that. We'll do the one at 4 because if you notice at 4, you're sitting at 4, back siding 3, foresiding 12. You're actually turning that angle counterclockwise. Now that's, as I've said in class, you wouldn't typically do that because you wouldn't have some angles to the left and some right. That's just going to be a place of mistakes. Okay. So we'll do that. I just wanted to point out something. Look at this equation up here. Latitude is equal to northing minus northing. Notice this is the same equation if I just bring this guy over here. So you can see how these equations are essentially the same. They're just rewritten. Now they're not for the same point, but so this is an inverse and this is a direct. Okay. That's where it gets the term inverse right there. You're inversing this right here. Process. You're changing it up. Okay. All right. So let me put the point for point 4. Okay. So in this case, I'm going to try to diagram it like it shows. We've got 4 sitting down here somewhere. 3 is kind of up here. And then we've got 12 sitting like over here. Again, not to scale. So this is point 12. We don't know his northing and easting. This is control point 3. We do know his northing and easting. So we have 1197.70 northing and 735.31 easting. So this guy right here, we measured this angle. We know that distance. Let's see, this is 4. I'm going to cram this in here. Let's see, that angle at 4 was 304.30.00. And we also know the coordinates at 4. They're 10, 15, 45, and 7, 13, 45. And the only other thing we know at 12 was the distance. That was 2980, that line. Okay, so that's what we know. Again, assuming north is up. Now, if this is if this is the azimuth which we're after, which it is the azimuth we need that azimuth. Since this is going counterclockwise, that would be a subtraction. What else could you do if you didn't want to mess with the subtraction? What could you do to make that simpler?
Find the internal angle.
Yeah. And yeah, so instead of using this guy, we could just do what? Solve that,
Subtract from
right?
360.
Yeah. And I think that would probably be easier. So that's what I'm going to do. Instead of messing with all that negative, I'm just going to go with that one. So let's take the 304, 30 and subtract from that from 360. I get this guy at 55 degrees, 30 minutes and 0 seconds. So hopefully you can see that was just an easier process to even deal with. I wouldn't even mess with that. I just get rid of this. Okay, does that make sense?
Yeah, it does.
Okay, so, well, let's just do it real quick. Let's finish it. So we started it. So what do we need to do now? That first.
Find the latitude and departure.
Yep. Of what?
4 to 3.
Yep, 4 to 3. That's good. 4 to 3, which would be the northing of what? 4 minus 3?
Yeah.
Nope.
3
No,
minus
it'd be 3 minus 4.
Correct. All right. And departure would be the same thing. Just remember, if you're going 4 to 3, you're just reversing it. If you remember that, you will definitely never make a mistake. And the thing is, like I said, if you do reverse it, you get the right number. It's the absolute value, though, and then that's gonna give you problems. So, all right, let's see what we've got. We've got the northing of 3 is 1197.70 minus 1015.45. So this guy's at 182.25. And I forgot to leave room. That should be a plus. And it looks like this one's going to be plus as well. Easting of 3, 735. Again, anybody see a mistake, check me on that. 713.45. Okay, and I come up with a positive 2186. Anybody agree with those numbers?
Yeah, I do.
Yes.
So again, this is nice because again, this is telling me positive that my bearing is northeast, right? So my bearing 4 to 3 is the arctangent of the departure 2186 over 182.25. Departure over latitude. Did I do that right?
Yeah.
When do you get a number?
I got 6 degrees,
6 degrees,
50 minutes, 23 seconds.
50 minutes, and 23 seconds. Does that sound right?
Yeah.
And we said that that would be what? Northeast.
East.
And so since that's a northeast quadrant, that's the same thing as an azimuth, so we don't have to convert anything. I can just write that over here. This is 6 degrees, 50, 23. That's my azimuth then. Okay, so to get my foresight azimuth, this one's real simple, isn't it?
You just add them.
That's what we're after. So what would that foresight azimuth be? So the azimuth 4 to 12 is going to be 6 degrees, 50 minutes, 23 seconds, plus 55.30. So if we had used this other angle here, we would have had this add that to a negative angle. We would have gotten a negative angle, which then we probably would have had to convert back. This just simplified everything. So if we add those, looks like 62 degrees, 20 minutes, 23 seconds.
Yeah.
And that's the azimuth. So that's this guy down here. In this case, 62, 20, 23. Okay? So there's my inverse up here. We did an inverse. Inverse that. Got the foresight direction. Now we need to get what?
That's the departure.
Yep. From latitude from 4 to 12 and departure from 4 to 12. So again, same equation. And this is my direct routine, what I'm doing right now. So I know my distance, 2980 times the cosine of my direction, 62, 20, 23. Okay, so I have cosine 62, 20, 23 times 2980 gives me a plus 1380, 83 it looks like. Everybody agree with that?
Yeah.
Okay. And for our departure distance, 29 sine 62, 20. And that should be a plus as well. Let's see what we come up with. Sine 62, 20, 23 times my 2980. I get a plus 2639. Okay, so again, same exact process. It's very streamlined. It's very methodical. Provided you just follow the steps. So the last thing now is to solve the northing of 12 and the easting of 12. So again, we know the northing of the point we're coming from, that's 4, plus the latitude that connects them, 4 to 12. So we have, let's see, we've got 10, 15, 45, plus a latitude of 1383. It looks like 10, 29, 28. 10, 29, 28. And then this guy will be the easting of the point we're coming from, plus the departure of the point we're coming from there. Okay, so that gives us 713, 45, plus the departure of 2639, 739, 84. There's my northing, there's my easting. That's what we're after. Right. So it's very much just a step process that you deal with. So those are side shots, and they're good because they encompass both direct and inverse routines. And on this lab, if we get to do it this week or whenever we get to do it, we're not going to be doing side shots. So we're going to be doing traverse closure stuff. Okay. Any questions on any of that? No questions? We're good?
Yep.
All right. So I gave you another problem, and it showed you, here, let me just draw it real quick. And we'll just see if anybody got an answer. So it had a station 1 and a station 2 point. And there was a property corner like over here. And another property corner like over here. And we couldn't see between these two property corners because there were obstructions. So that's kind of what that picture looked like. We called this point, we'll just call it 2, called this point 1, measured an angle and a distance to this property corner. We'll call that property corner, and this property corner, we'll just call that property corner 10 and property corner 11. So did anybody determine the distance on that? That's what we were after. We wanted to know, what is that distance? Did anybody get a distance? Nobody was able to get the distance?
I don't have the handout, so I wasn't able to work on it.
Okay, well, no, actually the handouts, yes, I don't know if the folder I just turned on today, so it probably wasn't on there, that's correct. I might have been on 3. If you are missing stuff, by the way, make sure you check Blackboard, because a lot of that stuff's posted, okay? Or you can always ask me, anybody. Did anybody get an answer for this?
I started, but then I got confused, so I just,
You're really low, could you turn up or something? I can't hardly hear you.
I started to do it. And then I confused myself, so I
Okay,
I stopped.
all right, do you want me to go through it?
Yes, please.
Okay, sure. All right, so we're missing a bunch of information, okay? So let me put all the information that we have on this picture. All right, so we said that, okay, these guys set up and they measured angles. So they measured an angle here of, let's see, this one was 41 degrees, 46 minutes, and we measured a distance to that property corner of 2592, okay? They measured a distance between 1 and 2 of 1,200, I'm sorry, yeah, 1,269.87. So a really nice long site. They measured this angle here of 110 degrees and 7 minutes. And this distance was 21.05. Okay, so that's what we knew. Now, we don't really know where north is on this, and we really don't care, because at the end of the day, we just want to know what is the distance from property corner here, which I'm just arbitrarily calling 11, to property corner 10. So I just want to know that distance. Okay. So what I suggested to you guys is, well, just assume a coordinate at one of these points and also assume a direction. So to keep it simple, what I think we kind of said in the class was, why don't we just arbitrarily call 1, 1,000, 1,000, northing and easting. And we're going to arbitrarily call this 90 degrees. So in other words, what I'm saying is north is straight up. But if I'm saying 90 degrees, I'm saying north is up. Because I'm saying this 1 and 2, they're just due east-west of each other. Okay. Well, there's a couple of reasons of, what was the reason of making this 1,000, 1,000? I mean, I wouldn't have to use 1,000, but what was my reasoning there?
If it's 90-degree east, the other station would just add the distance to it for the east thing.
Yeah. But what was I agree with that. But my question was, why did I use 1,000, 1,000 for 1?
Try to keep it in the positive coordinate.
Correct. And I don't want to call that 1,000.662 or something. I want to keep it simple. So also, and you brought up, if this is due east, that means this is my departure and there is no latitude, okay? So what that means is the northing of 2 is simply 1,000 because they're on the same point, right? And this distance is going to become 1,000 plus that 1269. So this becomes 2,269.87. Okay, so we're just trying to simplify everything. That's what we're doing. So we can solve a coordinate of 11 now really easily because we already know the azimuth from 1 to 2. So we can solve the azimuth from 1 to 11. That's simply going to be 90 degrees plus 110.07. And so we have simply what? 200? So we get 200 degrees and 7 minutes. That's my azimuth. Everybody agree with that?
Yes.
Yep.
Okay, so now very simply, all we need to do is a latitude from 1 to 11. It's going to be the distance, 2105, plus the cosine, cosine 200. So I'm coming up with a negative, and if I want to, excuse me, if I want to hold precisions out a little bit better, I mean, I can round my numbers out to a couple more places, but I came up with 19.766 essentially, if I go out that far. Departure, (2105), sine, same azimuth. And that one, I believe, is also going to be negative. If I round that to 4, that's or 3, that's what I'm getting. Anybody agree with those numbers?
I agree.
Okay, so if we now can solve very simply the northing of 11 is going to be equal to the northing of 1 plus the latitude 1 to 11. And you can see all we're doing is subtracting that 19,766. So we get 9802. Whoops. Yeah, that's right. 234. Whoops. No, it's not. It was 1 decimal over. 980. 234. My easting of 11 is equal to the easting of 1 plus the departure. So again, we're just subtracting the 7.24 from that. So we get 992,760. All right, so we're going to do the same thing up here now. What is my azimuth from 2 to 1 now? It's going this way now. What happens to this guy? Flip the azimuth.
Going in.
How do we what? Did I hear somebody say 180? we flip an azimuth by 180?
Subtract or add 180, depending on if it's greater or less.
Correct. So in this case, we're adding 180, right? So that gets us, this arrow flips this way. So when you add 180 to 90, you get 270, which should make sense because west from an azimuth standpoint is 270. So this guy just becomes now 270 when I flip it. That's another advantage of using what I did. All right, so now my azimuth from 2 to 12 or 10 is just going to be 270 plus 4146. 311.46. You guys agree with that?
Yep.
Okay, so my latitude, I'm running out of room here on my right. 2 to 10 is the distance 2 to 10 times the cosine of 311.46. And that's going to equal, now it looks like it should be a positive number. Get a plus 17.265. And then departure 2 to 10, 2592, sine of 311.46. And that should be negative because we're traveling west. But the calculator, when you do the math with the azimuth, is going to tell you that. So we get 19.333. So my northing of 10, northing of 2, plus that latitude, 2 to 10, and the easting of 10, easting of 2, plus the departure 2 to 10. So for my departure, it looks like I got 2,250,537. You guys check my numbers just to verify. $1,017,265. So I'm going to write that up here because I'm going to have to clean my stuff up a little bit here. Anybody agreeing with those numbers?
Yes.
I am.
Okay. So again, it might seem like we're doing a lot of work, and in some respects we are, but this stuff actually is pretty foolproof if you go through it and understand. Obviously, you know, we have other digital devices that do this stuff for us, but this is what it's doing, and this is what you need to kind of get a handle on. That's my coordinate there. All right, so all of that, ultimately, we're doing that because we want to get now the distance. So I'm going to get a distance from corner to corner. Looks like whoops, I need to undo something. I deleted some of my coordinate. Redo that. didn't want to delete my coordinate. Okay, so we know the northing and easting of property corner 10 to 11, so now we can inverse and we can get a distance. So simply, if you get a latitude, and it doesn't matter which way we go here, if I go 11 to 10, that's 10 minus 11. I'm not going to worry about the sign so much, but there is a sign if you're dealing with angle, but angle, we really can't tell much about direction, I guess I should say. That's 980. Looks like I got 37. I better check my number. Anybody get that? 37031? Does that sound right? So we've got,
Yeah, that's right.
okay, cool. That's good. 992.760. So that gives us 1257,777. So since we want the distance, now we can just use the Pythagorean theorem. So we're going to take and square the latitude and square the departure, and then take the square root of those sums. So when I do that, I get 1,258 point, I could probably round it back to 2 decimal places now. 1,258, that's an 8.32. So it's a lot of work, but it's pretty foolproof. And you know, you could probably cut some corners. I'm writing everything out, which I certainly suggest that you guys do, because that's all pretty important. Okay. So we want to make sure that you guys get a handle on this stuff. This is really, really important. Okay. Any questions on that?
How can we determine the direction just from those 2 points using the coordinates?
Well, you mean when this 270, you mean up here?
Well, if we were just gonna use the inverse routine for those 2 coordinate points,
Yeah.
and that's all that we had, would we be able to do that?
Well, if I can get a distance, no problem, right? That's going to be what it's going to be. The bearing, I could solve a bearing using these two guys. Okay. Departure divided by latitude arctangent. The problem with that, it's relative to whatever I called this up here. Okay. So since I just guessed that was 90 degrees, this bearing is going to be related to that line. That's fine, but it's not necessarily exact bearing of what it should be because we just assume something. Does that make sense?
Yeah, so we wouldn't just use that to solve it on its own. We would want to be
Right.
more exact.
Yeah, if we needed, but here's the other thing you could do, and we do this all the time out in the field. If I don't really know what a direction is, I just assume something. Later on, I can take my figure and rotate it. Okay. So once I figure out, once I figure out that this line is not north, let's say it's actually 81 degrees, 12 minutes, and 32 seconds. the distance between what I called it, or the angle between what I called it and what it is, that's my rotation angle. So I could rotate everything by that amount. But in this case, we weren't looking for that, so it didn't really matter. Okay, does that make sense then?
Yeah.
Because if you were explicitly looking for just distance, which we were, then we didn't care. But if direction was important, we'd have to be related to something somehow. So we would have to know what this direction from 1 to 2 truly was. Okay, or be able to get it at some point so that we could rotate it. Either way. But honestly, when surveyors are out there working a lot, they don't necessarily know their direction. They don't necessarily care because they don't need it, or we can rotate it after the fact, one of the two. Okay, so that was a good question. And again, it just depends on what you're doing. So, but for this case, we didn't care. Okay. All right, you guys kind of getting the idea? You're going to be doing a lot of this kind of thing. And if you can master that, that's really good process. Okay. So let me show you a radial stakeout problem, because this is you're going to be working on some of these problems for homework out of chapter 15, and one of those is a radial stakeout problem. So let me review that real quick. So again, it's going to be a lot of the kind of stuff we've already done. You're not going to see anything new. It's still going to be using inverses, but it's not. You wouldn't classify it as a direct routine at all. It's all inversing in this process. So here's what we're saying. We'll get an example here. We've got a point sitting over here that's a control point, and we've got a point sitting over here that's a control point. And we have a manhole sitting over here that we need to stake to. So we need to stake that out. I'll just keep our numbers simple so we can see this process. So we're saying this is a control point. This is point 51, and this is a control point, and this is point 50. And 50 is 5,000 north, 5,000 east, 51. I'll just keep this simple. 5,065, we'll call it. Now remember, those are usually going to have more decimal places than that, but we're just keeping it pretty easy. So we have a manhole over here on the set of plans. This is a manhole, has a coordinate on it, so we need to stake it. Let's say this manhole, and a lot of times people will use numbers for different purposes. So like we would call all of our points 300 on our project are either sanitary sewers or catch basins or manholes or something. And then you might use like series 200 for buildings and series 400 numbers for parking lots. So people kind of do it that way to keep everything straight. So let's say this does have a coordinate of 49, 78. We'll just call that 775 northing. That's a 9 right there. And this will be 49, 28.452. So that's in term northing, easting, northing, easting, northing, easting. So now, so if you were using GPS, what you would do is you would get on your site with GPS, you would basically key these control points in, maybe occupy them for a minute or two, what they do called a calibration, make sure everything's working. And then you key these coordinates in your GPS controller and it navigates you right to it. It'll say, go this distance, so many feet, turn left, whatever, and then it'll walk you right to it. So we're going to assume we don't have that capability. What we're going to do, we got a total station. We're going to set the total station up at 50. So we would say we're going to have the instrument at 50. We want a back site 51. And we want a foresight 301. So what we need when we do this, we're going to need the angle. And we'll do the angle to the right. And we need the distance. So this process is what you call radial stakeout. And so we're going to calculate this angle to the right and this distance from 50 to 51. So anybody tell me how we do this? Well, how can we get an angle between these 3 points? Known coordinate, coordinate, coordinate. Any suggestions? Well, we've already done this.
We need the distances.
Say that again?
We're going to need the distances.
Well, we only need the distance from 50 to 301, okay? But to get the angle, what are we going to need? I want to know what this angle is. So I want to set my instrument up at 50, backsight 51, set zeros on the scope, and then turn this angle so that I can go to that manhole. So how can I get an angle?
Latitude and departures.
And what is that going to give me? I agree. What can I get from the
I think-
latitudes? Go ahead.
Azimuth.
Azimuth.
Or- yeah.
Yes, azimuth. Correct. Now you won't get an azimuth, will you?
No.
You get a bearing, right?
Yeah.
So we're going to get the bearing from here to here, which we can convert to an azimuth, and we're going to get the bearing from here to here, which we can convert to an azimuth. And once we got azimuths, we got our angle. Okay. So again, the process is an inverse. So I'm gonna, let's see how quickly you guys can set this up for me. I'm gonna just delete this real quick. So ultimately that's what I'm after. And that guy, so I'm gonna want the, first off the bat, I'm gonna want the azimuth, the bearing, let's say from 50 to 51. So I'm gonna want the latitude. I'm gonna not write everything out this time. I want to go 50 to 51. So what would I subtract?
The northern of 51 from the northern of 50.
Right. So we're going to have 50, 65 minus 5,000. Okay. Well, you can see what's that give us, what? Plus 65.00, right? Departure 50 to 51 will be the easting of 51, 4759 minus 5,000. Now that'll give us a negative number, and that should be apparent, assuming north is up, why that would be negative, because it's looking which direction?
West.
West.
Correct. And so that should make sense. So we should have a negative 241, it looks like.
That's what I got.
So, all right. So knowing departures and latitudes, get that bearing, arctangent. Departure is 241. Latitude is 65. Okay. Swing those over. Let's see, 241 arctangent. Looks like 74 degrees, 54.21, northwest, right?
Yeah.
Which would equal what azimuth?
Fifty to
360
51.
minus that.
360 minus that, right? So what's that give us? You guys check me. $285.0539. Does that sound right?
Yes.
Okay. All right, so there's my there's my backside direction. So I need my foresight direction. I'll write that down here. Latitude. This time I want to go 50 to the manhole, which would be to 301. So that's the northing of 301 minus the northing of 50. So we have 49, 78, 775 minus 5,000. 21, 225. Departure. That would be the northing or the easting rather of 301. $49.28, 542 minus 5,000. Yeah. Well, the answer I got wasn't right. Looks like a minus 71,458. So everybody agree with that?
Yes.
All right, so my angle here would be the arctangent of departure over latitude. It's like 73 degrees, 27, 26, looks like. South, negative, west, which would give me an azimuth. Did anybody agree with my angle, by the way?
Yeah, I do.
Okay, so how do we get that azimuth?
Add 180.
Yeah, that's a very simple. When you're in that quadrant, it's real nice. It's kind of like being in the other quadrant, northeast. So this gives me 2, 53, 27, 26. All right, so we needed this angle right here, we said. The angle to the right, sitting at 50, backsighting 51, foresighting 301. So how could we do that now? Well, you know this direction. This is actually, we know that azimuth there. We know this azimuth.
Yeah, so the first azimuth, you could subtract that from 360 and then add that to the azimuth of the one that we just did, and then that'll give you that whole entire angle.
Oh, that's cool. So everybody see what he said? Said, look, if this is north, we know this angle coming around. If we subtract that azimuth from 360, which would give us 74, 50, 421, right?
Yeah.
We just add that to this azimuth right there. So that would work perfectly. So what we're saying is if we recognize we got 74, 54, 21, and we add to that 25, that would be my angle to the right. So let's see what we come up with. Let's see, I got 74. Yeah, that was very nice the way that, because we already had everything written out, so we could use that really readily. Looks like the angle you would turn from the instrument would be what, 328, 2147. Okay. Anybody see another way you could do it? I was actually going to do it a different way. But do you see another way you might do that? If you know this azimuth is 253, this one here is 253, and this one is 285, you can subtract these two, and it would get you this angle actually. And then you'd have to subtract that from 360. So really, it's about the same amount of work. It's just that was really slick because we already had this. Recognizing that's there, we just added them. That's the angle we were after. How do we get the distance to the manhole?
The difference.
The difference.
So I was going to say something, but I was going to say it wrong.
Okay, that's all right. You can say it wrong. Now we're going to use a Pythagorean theorem. We've got latitude and departure from here to here. So we would square that plus that squared, take the square root of those sums, and that'll give you the distance. Okay. So that's using inversing, but that process, we would call this process radial stakeout. Okay. So, I mean, I hope you guys are starting to see, appreciate, there's a lot you can do with this. The more you do it, it gets easier. Okay. It does get easier. All right, let's take a look at a couple more things, and then I get you out of here. The last thing, so what we talked about, we covered this quite a bit today, on the lab last time. Make sure you're doing this homework, okay, so that you're okay with that. So I just went over direct and inverse routines today. I just showed you how to do an angle plus a distance. So that would be a radial stakeout. We're not going to do intersections, okay? We just don't have time to do intersections. But I do want to show you this little slick thing you can do with area. If you've never seen this before, area works pretty cool using coordinates. So let me see if I can buzz through that. All these equations we've been doing are in here. They're in your book too. You don't have to worry about the analytic geometry. I've given you that, but basically make sure you're focusing in on the surveying stuff. Okay, so this is how you do a coordinate calculation. It's really cool. You can either use northings or eastings. So what you do, if you have, let's say in this case, I have 3 points, point A, point B, and point C. Say you got a triangle. What you're going to do is you put your eastings on one side, A, B, C, and your departures or your northings on the other, or I'm sorry, latitudes, or your northings on the other, Y's, A, B, C. And then if you start at A, you have to end at A. So I'm going to copy. Notice I start at A with the Y, I end at A, start at A in the X, and end at X. So what you do is you multiply X of A times Y of B, okay? And then you're going to add to that X of B times Y of C. And then you're going to add to that X of C times Y of A. So you get this product plus that product plus that product. And then when you go the other way, you're going to multiply Y of A times X of B, but you're going to make that a negative product. And then you're going to do a B, Y of B times X of C. You get another negative product. And you're going to do the same thing here. And when you sum all these up, what it's going to give you is twice the area. So when you get done with your total solution, you just divide everything by 2. It can be kind of messy if you got a lot of coordinates, but it really works very slickly the way you do it. I'll just show you this real quick. And then if we don't get this state plane, I'm not really worried about it because we're not going to do anything with it, but I'll probably talk a little bit more about it later. Let's see if I have a little example for you for this, because this is actually a really neat little process. We'll just make something up real quick. So let's say we've got a triangle. And let's say this point here I'm going to keep them pretty small. Let's say that this is, I'm going to say that this is 100, 200. And we'll call this, let's see, just got to think about this. This will be, we'll call this 200, 150. Wait a minute, got that reverse, I think. Got to think about this. This is, we're going to call this 50 because this is more south. So this is in terms of northing easting, and we're going to call this 250. And I'm going to call this 200 northing, and that'll be right in the middle essentially. So that'll be 225, we'll call that. So these are all in terms of northing easting. So if we start, let's say, we'll call that 1, 2, and 3. Now again, notice north is up in here because that's getting higher and that's getting, yeah, okay. So what you do is you can start, it doesn't matter whether you put the northings first or the eastings first. So I'm going to start with the northings. So I'm going to start with 1. So this is 1, 2, 3, and then I have to repeat 1. So 2's northing is 100, and then that's 50. So if I start at 200, I got to end at 200. So the eastings, we're going to have 225, 200, 220, 250, and then back to 225. Okay, so this is northing to northing to northing, northing to northing to northing, and then back to northing, and then easting, easting, and easting, back. So you start out and you just multiply like this. So we would have 200 times 200 plus 100 times 250 plus 50, 225, and then you go backwards, but we're going to call this a negative product. So that'll be 225 times 100 minus 200 times 50 minus 250 times 200. And the way I always check myself when I do this setup is if I start at 1, I have to end at 1. So I should have 1, 2, 3 positive products, 1, 2, 3, and then 1, 2, 3 negative, 1, 2, 3 negatives. When I do this math, and it does get a little messy, but it's going to be 2 times the area. So to actually get the area at the end, you just divide that whole mess by 2. It's actually pretty slick. It works pretty well. If you have a program, like probably a program like AutoCAD does something similar to this when it does calculations, it can do it very rapidly. Or even in an Excel spreadsheet or something, you could do that really rapidly. And it sometimes, depending on which way you go, if I reverse this and make these the negatives and that's the positive, you can get a negative area, but that doesn't mean it's incorrect. So it just means that it just means whether you went around it clockwise or counterclockwise. That's all it means. So that's a coordinate by area calculation by using coordinates. Otherwise, to do something like that triangle would be a little bit of a mess. That's not an easy triangle to solve if that's all you had. So you would be able to solve that pretty easily using that method. So that's a pretty cool little trick to know, and that's actually, he covers that in chapter 15. So let me go back to let's go back here. So let's kind of recap. What we want to do is I want you to work on some of these coordinate calculations between now and Thursday, depending on what we're gonna do yet. I still haven't decided. I'm kind of on the fence. I really want to go out in the field with you, but I'm just gonna have to play it by ear. I'll see tomorrow. I've got to go over to the college and I'll see what the field's gonna look like. And as soon as I figure that out, I'll let you guys know. So I'm gonna let you know pretty early on Wednesday. So, but just count on Thursday going out for now. But if not, what I want you to do is look at chapter 15. There's chapter sections to read. Let's see, the reading is for 15. There's your reading. So you've got that in your syllabus. And I would like you to tackle those problems out of 15. There's problem 16, problem 18, problem 21, and problem 46. All right. And so I would review those next Tuesday, and then our test will be that following Thursday. Also, I gave you guys some problems out of chapter 14. There's two traverse problems, problem 13 and problem 16. So we didn't have a chance to look at those today, but that would be another thing I will finish off with on, if, like I said, if we end up going in class on Thursday, we'll just go over this stuff on Thursday. So try to look at this chapter 14 and 15 stuff between now and Thursday, but also kind of be prepared for that. I haven't posted the lab out there yet, but I'm going to give you guys a lab handout. I'll probably have that posted either tonight or tomorrow also when I give you the announcement. So be looking for that announcement. Okay. Does anybody have any questions? No questions? Okay, I still have a couple guys I need to get quizzes to for quiz 1 and 2. I know who needs those. So as soon as I get those set up on Blackboard, I'll be posting you guys an announcement. Probably be tomorrow, and then we'll probably also have a quiz on Thursday or sometime this week or maybe the weekend. So I'll be getting a quiz 3 out there for everybody. And if we come to class on Thursday and meet in 152, you'll get the quiz in class. Otherwise, I'll just post it on Blackboard. But again, I'll let you guys know either way. Okay. So any questions then before we terminate it today? Any questions about going outside if we go outside? Just remember, there's going to be a lot of snow out there, so you've got to have some kind of good boots that you're going to not get cold and wet. All right. Temperature might be a little low, so make sure you're dressing in layers if we do go out. All right. No questions then?